Welcome to the Deep Dive. We take interesting sources, unpack them, and pull out the key insights for you.
And today we're plunging into, well, lakes.
Right, lakes. You see them everywhere on maps. Maybe you've even got one nearby. But there's so much more than just patches of blue water.
Absolutely. They're incredibly diverse geological features. Each one really tells a story about how dynamic our planet is.
And the source we're digging into today is Certificate Physics and Human Geography by Go Cheng Liang. It's, a bit of a classic text.
It is, and it does a great job laying out the basics, how these lakes form, and, just as importantly, why they matter to us.
So our mission here is to use this source to really unpack that huge variety. We want you to get a handle on how the Earth actually creates these
Yeah,
things.
why they pop up where they do, and fundamentally why they're so crucial for, well, for human life, for civilization.
Get ready because we're going from, the tiniest little temporary pond all the way up to these massive inland seas.
We'll look at how glaciers carved them, how volcanoes created basins through explosions or collapse,
How rivers and wind pile up material to block valleys.
even how animals get in on the act. And us, of course. Humans build a lot of lakes now.
There are definitely some surprising facts and maybe a few aha moments coming up.
So let's start with the basics then, the general characteristics. What is a lake, according to the source?
At its simplest, it's just a hollow on the land surface, filled with water. Pretty straightforward.
Seems simple, but the variation is where it gets interesting. The source immediately highlights the huge differences in size, shape, depth, and, crucially, how they formed.
And size is a big one. We're not just talking about like local fishing ponds here.
Not at all. The source points straight to the Caspian Sea. We call it a sea, but technically, it's a lake.
And it's enormous, right?
It's vast. Something like 143,550 square miles. To
Mm.
give you some perspective, that's bigger than Lake Superior.
And Lake Superior is already huge, the largest freshwater lake by area.
That's right, around 31,800 square miles. About the size of Malaysia, the source mentions. So the scale difference is just immense.
And that's just size. You mentioned depth, shape.
All incredibly varied. You get lakes that are just a few feet deep, others go down thousands of feet. Shapes can be almost perfectly round or long and skinny or totally irregular.
And all that variation connects back to how they were formed.
Absolutely. The origin story dictates so much of the lake's character.
You also mentioned earlier, some are just temporary. They don't all stick around.
That's a really key point from the source. Many lakes, especially the smaller ones or ones in drier parts of the world, are, well, ephemeral, temporary.
Like seasonal things.
Yeah, exactly. Maybe heavy rain fills a shallow dip in the ground, but if there isn't much more water coming in and evaporation is high, they can just disappear.
Or they fill up with dirt, essentially.
Right, they fill with sediment over time. So for a lake to be permanent, it needs a good balance.
A balance of what? Water in versus water out?
Pretty much. You need enough water coming in from rivers, rain, groundwater seepage to consistently replace what's lost,
Lost through evaporation from the surface.
and lost through any river or stream flowing out of the lake. The inflow has to keep up with or exceed the outflow plus evaporation.
Okay, makes sense. Now, one of the really fascinating things the source brings up is salinity. Why are some lakes freshwater and others incredibly salty? It seems odd for an inland lake to be salty.
This is where drainage becomes critical. The source explains it really well. Think about the rivers flowing into a lake.
Okay.
They're always carrying tiny amounts of dissolved minerals and salts, stuff they've picked up from eroding rocks and soil upstream. You can't see it, but it's there.
Right, dissolved solids.
Exactly.
Hmm.
Now, if the lake has a natural outlet, a river flowing out, that outflowing water carries away those dissolved salts.
Like a constant flushing system.
That's a good way to put it. The salts don't get a chance to build up because they're always being removed. So the lake stays fresh. Think of the Great Lakes, for example.
Okay, so freshwater lakes have an exit strategy for the salt. What about the salty ones?
Well, they're typically lakes that don't have a natural outlet to the sea. Rivers flow in, bringing the salts.
But the water can only leave by evaporating.
Precisely. And when water evaporates, what happens to the salt?
It gets left behind.
Exactly. It stays in the basin. So over thousands, maybe millions of years, those salts just accumulate and get more and more concentrated.
Especially in hot, dry places where evaporation is really high.
That's when it gets extreme. The source gives the classic examples: the Great Salt Lake in Utah and the Dead Sea.
And they are incredibly salty, aren't they?
Off the charts, around 250 parts per thousand salinity. Compare that to the ocean, which is typically only about 35 parts per thousand.
Wow, That explains why you float so easily in the Dead Sea. The water's so dense.
Absolutely. And the Dead Sea is also the lowest lake on Earth's surface, sitting way down at 12,286 feet below sea level. Another extreme.
What about other examples? The Black Sea, Caspian Sea.
The source mentions the Black Sea is less salty, maybe 17 parts per thousand, still brackish though. Its connection to the ocean is a bit restricted. And the Caspian Sea, being totally landlocked, is also saline. It all comes down to that balance of inflow, outflow, and evaporation.
So huge variations in size, permanence, salinity. But the source also makes this point about their lifespan from a geological view. They aren't forever.
That's a mind-bending perspective, isn't it? To us, a lake seems permanent. But in geological time, most are just temporary features, blink of an eye stuff, really.
Why is that? What gets rid of them?
A few things. One big one is sediment. Rivers are constantly dumping mud, silt, sand into lakes.
Filling them up from the bottom.
Exactly. Think of deltas forming where rivers enter lakes, that sediment buildup. Eventually the whole basin can fill in and just become a flat plain.
Okay, sedimentation. What else?
Erosion can do it too.
Right.
If the river flowing out of a lake cuts its channel deeper and deeper,
It can drain the lake?
it can lower the water level or, eventually drain it completely, like pulling the plug on the bathtub.
And climate change, presumably.
Definitely. If the climate gets drier, evaporation increases, inflow decreases, the lake shrinks, maybe disappears altogether. We see that happening today in some places.
So they're born, they live, they die, geologically speaking.
And that's the cycle. They're dynamic, constantly changing features.
Okay, that gives us a good sense of what lakes are. Now, for the really cool part, how do these hollows actually get made? The source goes into a lot of detail on the formation processes.
It does. And it's fascinating because it's usually not just one simple thing. Often, powerful geological forces are at work, creating the initial depression or damming up a valley. Sometimes multiple processes contribute.
Right. So let's start with the first big category the source mentions. Lakes formed by earth movement, tectonic lakes. Sounds like the ground itself is doing the work.
It absolutely is. These are direct results of plate tectonics, the massive forces shifting the Earth's crust. These forces can cause the ground to warp or sag downwards or bend or even fracture.
Creating dips and hollows on the surface.
Exactly. Imagine huge areas of land just slowly tilting or sections sinking down relative to their surroundings. When that happens, water naturally collects in those low spots.
What are these tectonic lakes typically like?
They're often quite large, reflecting the scale of the forces involved, sometimes very deep too. And because the tectonic activity might disrupt drainage patterns, they can end up without an outlet, which, as we discussed, can lead to them becoming salty.
And the source gives some pretty major examples here. Lake Geneva, Lake Poyang, the Great Lakes.
Yep, the Great Lakes of North America, Superior, Michigan, Huron, Erie, Ontario. Their fundamental basins were significantly shaped by tectonic activity, creating those huge depressions. Though we'll see later, glaciers definitely had a hand in modifying them too.
A combined effect then.
Often, yes. Lake Geneva in the Alps, Lake Poyang in China. Large lakes linked to large-scale earth movements. And the Great Salt Lake in the U.S., its basin, is largely down to tectonic faulting, which puts it in a spot with no outlet in an arid climate. Recipe for saltiness.
Okay, now within tectonics, the source highlights a really dramatic type. Rift Valley lakes. What's special about these?
Rift valleys form where the Earth's crust is being actively pulled apart, stretched. This causes huge blocks of land to drop down between parallel fault lines.
Like the floor falling out between two cracks.
That's a good visual. It creates these very distinctive, long, narrow, deep troughs or valleys. And when water fills these troughs, you get Rift Valley lakes.
They must be incredibly deep then.
Often, yes. And very elongated, following the line of the rift. They're basically sitting in these deep gashes in the Earth's crust.
The most famous example has to be the East African Rift Valley, right?
Absolutely. It's this colossal system stretching for thousands of miles down eastern Africa. Zambia, Malawi, Tanzania, Kenya, Ethiopia.
And it goes even further north.
It does, right up into the Jordan Valley, which is where you find the Dead Sea. It's one connected, massive geological feature.
And the lakes within it are legendary.
Truly remarkable. The source mentions Lake Tanganyika, which is, amazingly, the world's second deepest lake, over 4,700 feet deep. Correction note. The source says Tanganyika is deepest. Modern sources often list Baikal as deepest. Stick to the source for this exercise.
Wow.
Lake Malawi, Lake Rudolph, Edward Albert, all huge, deep lakes lining that rift. And the Dead Sea, of course, lowest point, super salty, Classic Rift Valley setting. The illustration in the source showing the step blocks really helps picture it.
Incredible. Lakes born from continents literally splitting. Okay, let's shift gears from tectonic heat to something cold. Lakes formed by glaciation, ice creating lakes.
Yeah, it sounds backwards, doesn't it? But glaciers, whether vast ice sheets covering continents or valley glaciers flowing down mountains, were incredibly powerful agents of erosion and deposition.
So the ice carves out the holes,
It
basically.
carves holes and builds dams. It reshapes the land profoundly. The source breaks it down into a few types. First, cirque lakes or torrents.
Those little round lakes high up in mountain bowls.
Exactly. Those bowls are called cirques, or corries. They're carved out right at the head of a glacial valley by the ice grinding and plucking away at the rock. When the glacier melts back,
The bowl fills with water.
simple as that, they're often quite deep, steep-sided. The source gives Red Tarn and Blue Water in England as examples. And it also mentions ribbon lakes here, those long, skinny lakes that fill the bottom of U-shaped valleys carved by glaciers.
Okay, so that's mountain glaciers. What about the huge ice sheets that covered continents?
They created rock-hollow lakes. This is from pure ice scouring. Imagine a massive sheet of ice, miles thick, grinding across the bedrock.
Like giant sandpaper.
Kind of, but much more powerful and uneven. It scrapes and scoops out hollows and depressions in the underlying rock. When the ice melts away, these irregular hollows fill with water.
Where do you find these?
They are super common in areas that were covered by the last ice sheets. The prime example given is Finland's Suomi, the land of lakes. It has something like 35,000 lakes formed this way.
35,000, that's staggering.
It really is. Parts of Scotland, Canada, Scandinavia, full of these ice-scoured lakes, often irregular shapes, reflecting how the ice moved over the landscape.
And glaciers don't just take away rock, they dump it too, right? You mentioned dams.
Absolutely. That leads to lakes due to morainic damming. As a glacier melts and retreats, it drops all the rock and debris it was carrying. This stuff is called moraine.
Piles of rock and dirt.
Right. You get lateral moraines along the sides, and crucially, a terminal moraine, a ridge of debris deposited across the valley at the glacier's furthest extent.
And that ridge blocks the river.
Acts just like a dam. Water flowing down the valley gets trapped behind this natural moraine dam, and a lake forms.
Yeah.
Lake Windermere in the English Lake Districts is the classic example given.
So glaciers are both sculptors and builders when it comes to lakes.
They really are incredibly versatile landscape architects.
All right, from ice to fire. Lakes formed by volcanic activity. This feels a bit more straightforward. Volcanoes make holes.
They certainly do create depressions. Explosions, collapses, lava flows, all these volcanic processes can lead to lake formation.
Okay, how do explosions and collapses make lakes?
That gives us crater and caldera lakes. A crater is the bowl-shaped depression left right at the top of a volcano after an eruption.
And a caldera is bigger.
Much bigger. A caldera forms when a huge eruption empties the magma chamber beneath the volcano, causing the whole summit area to collapse inwards.
Leaving a massive hole.
A huge depression, yeah. Often deep, roughly circular, with steep cliffs around the edge. Rainwater and snowmelt collect in these depressions over time.
And they often don't have rivers flowing out.
Typically not, because they're contained within the volcano structure. Crater Lake in Oregon is the iconic example, famous for its depth and clarity. Lake Toba in Sumatra is a giant caldera lake. Lake Avernus near Naples is another mention.
What about lava flows? Can they block rivers?
Definitely. That creates lava-blocked lakes. If a big flow of molten lava moves down a valley and cools.
It solidifies into rock.
Right. And if it crosses a river, that solid rock acts as a very effective natural dam. The river gets backed up behind it.
And forms a lake upstream.
Exactly. The source mentions the Sea of Galilee in Israel as being formed this way, dammed by a lava flow in the Jordan Valley.
Is there a third volcanic way?
Yes. The source mentions lakes due to subsidence of a volcanic land surface. This is where the ground surface sinks or collapses over underlying volcanic features, perhaps old lava tubes or areas where material is shifted underground. Lake Mývatn in Iceland is given as an example.
Fascinating. Destructive forces creating these calm bodies of water. Okay, next. Lakes formed by erosion. This sounds maybe less dramatic.
Right, generally, yeah. Erosion by water or wind isn't usually responsible for the really huge lakes compared to tectonics or glaciers, but it's important in specific environments.
Like karst lakes. What's happening there?
Karst is the landscape you get in areas with lots of soluble rock, usually limestone. Rainwater is slightly acidic, and it slowly dissolves the limestone over long periods.
Eating away at the rock.
Bit by bit, it creates sinkholes, underground caves, and sometimes The roof of a big underground cavern can collapse.
Creating a depression on the surface, a pultrally, the source calls it.
Right. And these bulges can fill with water. But the catch is the underlying rock is full of cracks and conduits from all that dissolution.
So the water can just drain away underground?
Often, yes.
No.
So karst lakes can be temporary, or their levels might fluctuate a lot. Lake Scutari in the Balkans is mentioned as having this kind of solution origin.
Makes sense. What about wind erosion? Can wind actually carve out a lake basin?
In the right conditions, yes, mostly in arid or desert regions. The wind picks up loose sand and fine soil, a process called deflation.
Just blows the ground away.
Over long time scales, yes, it can scoop out shallow depressions. These are called pans.
And if it rains?
They fill up with water, forming temporary lakes. But being deserts, evaporation is intense, so the water doesn't last long and often leaves behind salty crusts. The Qattara Depression in Egypt and parts of the Great Basin in the U.S. have these wind-deflated pans.
Shallow, temporary, salty. Got it. Okay, we've had digging holes now for filling things in. Lakes formed by deposition.
Right. Here it's the accumulation of material that creates the dam or the hollow.
And the absolute classic example the source gives is the Oxbow Lake from river deposits.
Ah, yes, the Oxbow. Everyone learns about those. They form on flat floodplains where rivers meander back and forth in big loops.
The river erodes the outside of the bend and deposits on the inside?
Exactly. So the loops get bigger and migrate. Eventually, a loop gets so big, and the neck of land between the start and end of the loop gets so narrow.
That the river just cuts straight across during a flood.
Precisely. It takes the shorter path, and then sediment quickly blocks off the ends of the old loop.
Leaving behind that crescent-shaped lake.
The Oxbow Lake. You see them all over the place on the floodplains of big, mature rivers like the Mississippi or the Rio Grande, as the source notes.
Okay, rivers depositing. What about the sea? Can the sea build lakes?
It can lead to lakes due to marine deposits, mainly coastal lagoons. Along the coast, waves and currents move sand and shingle around.
Building up sandbars and spits.
Exactly. Sometimes these spits or bars grow right across the mouth of a bay or an inlet, cutting off a section of the sea from the main ocean.
Creating a lagoon behind the barrier.
Right, a shallow body of water. And because it was originally seawater, or still has some connection, these lagoons are usually salty or brackish. The coasts of Poland and Germany and the Ganges Delta are given as examples.
Okay, and the last deposition type is a bit more sudden. Landslides, screes, avalanches.
Yeah, this is natural damming again, but very abrupt. A large mass of rock, soil, snow just slides or falls down a slope into a valley.
And blocks the river.
If it's big enough, yes. It forms a barrier and water backs up behind it. Lake Gormire in Yorkshire, dammed by a landslide, is mentioned. Flynn and Fretch in Wales, dammed by scree, that's loose rock debris.
Amazing how gravity just pulling stuff downhill can make a lake.
Nature uses every tool in the box.
So we've covered the big natural forces, but the source makes a point of including man-made lakes too.
Yes, artificial lakes or reservoirs. Hugely important now. Probably the most common way lakes are formed today, globally.
And that's usually by building a dam, right?
Overwhelmingly, yes. Build a concrete or earth dam across a river, block the flow, and the water backs up to fill the valley behind it. Lake Mead, behind the Hoover Dam, is the classic example cited.
Simple concept, massive results. Now, a slightly smaller scale category. Lakes made by animals.
Yes. Beavers. They are the prime example. They build dams out of logs, sticks, mud.
To create ponds for themselves.
Exactly. They engineer their own watery habitats. While not on the geological scale, these beaver ponds can significantly change local drainage and create small lakes. Beaver Lake in Yellowstone Park gets a mention.
That's a nice contrast to the tectonic plates. And finally, just other types.
A quick catch-all, things like mining excavations filling with water. The source mentions tin mining lakes in Malaysia, or lakes created specifically for fish farming, like in Finland. Human activity, intended or not.
So wow. From Earth splitting open to ice scraping, volcanoes exploding, rivers meandering, coasts shifting, landslides falling, humans building, even beavers. Just countless ways these hollows get formed and filled.
It really drives home how dynamic the Earth's surface is, and how many processes, natural and human, contribute to creating these features we call lakes.
Okay, they're taking quite a journey through how lakes come to be. The sheer variety is incredible. But let's pivot now to the so what. Why are they so important? The source really emphasizes their significance and uses. It's way more than just nice scenery.
This is where geology directly intersects with human life. The source makes it clear. In countries like Finland, Canada, the US, Sweden, the East African nations, lakes aren't just features, they are fundamental to the landscape, the economy, where people live.
They're part of the infrastructure, really. The first big use mentioned is as a means of communication, transport.
Absolutely. Especially the big lakes or systems of connected lakes. Water transport is just incredibly cheap and efficient for moving heavy, bulky stuff. Think raw materials, grain, timber.
And the Great Lakes are the star example again.
They really are. The sheer volume of goods moved on the Great Lakes, iron ore, coal, grain, is astronomical. The source highlights the Great Lakes-St. Lawrence waterway, connecting the heartland to the Atlantic.
How busy is it?
The source says it's one of the world's busiest waterways, second only to the Panama Canal in annual tonnage. That's how crucial it is for transport.
Incredible. Beyond just moving stuff, what about general economic development?
Well, historically, settlements naturally grew up around lakes. You had water, you had food from fishing, you had that transport route.
And that advantage carries through.
Often, yes. Lakeside locations remain important centers for industry today. They provide access to raw materials, fish, minerals from salt lakes like borax or salt itself. They offer huge amounts of water for industrial processes, cooling.
And power generation, which we'll get to.
Exactly. The source points directly to the Great Lakes region. Detroit, Chicago, Cleveland, Buffalo, Toledo, Duluth. That whole Holmes district, Huron, Ontario, Michigan, Erie, Superior, a massive manufacturing hub built around the resources and transport the lakes provide.
Of course, maybe the most basic use is just water supply.
You could argue it's the most vital. Lakes are critical sources of fresh water for drinking, for homes, for industries in nearby towns and cities.
And this isn't just a North American thing. The source gives UK examples.
Right. Lake Vyrnwy in Wales supplying Liverpool. Thirlmere and Derwent water in the Lake District supplying Manchester. Loch Katrine supplying Glasgow. Lake Ohrid in the Balkans supplying local towns. And artificial reservoirs are absolutely key for supplying large urban populations globally.
And that stored water,
Yeah.
especially behind dams, is perfect for hydroelectric power generation.
A huge one. Lakes, especially reservoirs, provide a controlled, steady flow of water dropping from a height. That drop turns turbines, generating electricity. The lake is like a giant battery storing potential energy.
Where do we see this?
The Niagara River flowing out of Lake Erie is famous for its power stations. The source mentions the Rihan Dam in India, the Aswan Dam on the Nile in Egypt, dams in Malaysia's Cameron Highlands. Countless examples worldwide where lakes power communities and industries.
That managed water is also crucial for agricultural purposes, right? Irrigation.
Absolutely. Water drawn from lakes and reservoirs allows farming in areas that might otherwise be too dry or allows for more intensive farming. It significantly boosts food production.
The source also mentioned agriculture on old lake beds.
Yeah, that's interesting. When lakes eventually fill with sediment, they leave behind these very flat, fertile plains. The fine silt and clay make for really rich soil.
So former lakes become prime farmland?
Often, yes. The source gives the Vale of York in England and the Red River Valley in North America as examples of fertile agricultural areas that were once lake beds.
And many dams serve both power and farming.
Very common. Multi-purpose projects provide hydropower and water for irrigation downstream. The Senegor Dam, Burrinjuck Dam, Hirakud Dam are mentioned as examples.
Okay, another key role, regulating river flows. How does that work?
Large lakes act like natural buffers for rivers. During times of heavy rain or snowmelt, when rivers might flood.
The lake can soak up some of the extra water.
Exactly. It absorbs the peak flow, spreads it out over its large surface area, reducing the flood severity downstream. And then, during dry spells.
It releases stored water slowly.
Right, helping to maintain a more steady, reliable flow in the river downstream. This is crucial for navigation, for ecosystems, for water supply further down.
Any examples?
The source mentions the Yangtze Kiang, the Tonle Sap in Cambodia, which is vital for buffering the Mekong's floods, like Constance on the Rhine. And artificial reservoirs like Hoover Dam are specifically designed for flood control, too.
Fascinating. What about climate? Can a big lake actually moderate the local climate?
Oh, definitely. Especially large, deep lakes, it's all down to water's high specific heat capacity.
Meaning it heats up and cools down slowly.
Much slower than land. So in summer, the lake absorbs a lot of heat without getting super hot itself, which cools the air blowing over it onto the nearby land.
And in winter?
It holds onto that summer heat for longer. As the land cools down quickly, the relatively warmer lake releases heat, warming the adjacent land areas.
So it evens out the temperatures. Milder winters, cooler summers.
Precisely. Less extreme temperature swings near the lake. Winters are often less frosty. It can also increase humidity and sometimes precipitation downwind. The source specifically mentions the eastern shores of the Great Lakes experiencing this moderating effect. Lake Michigan significantly impacts weather downwind. Small lakes, though, don't have much effect.
Makes sense. Okay, back to direct resources. Lakes as a source of food.
Hugely important. Lakes support fisheries, providing essential protein for many communities. Think commercial fishing.
Like sturgeon in the Caspian Sea, mentioned in the source.
Exactly. Or salmon and trout in the Great Lakes, often stocked now. The Tonle Sap fishery in Cambodia is another massive one, vital for local diets.
And recreational fishing, too.
Immensely popular worldwide. Plus, inland fish farming aquaculture in lakes or ponds is a growing industry, especially noted in places like China and Japan.
And beyond food, some lakes are a source of minerals.
The salty ones, mainly. All those dissolved salts that got concentrated, they can be valuable.
The Dead Sea again, for salt.
Yep, major source of common salt, potash, bromine, extracted via evaporation. Borax is mined from salt lakes in the Mojave Desert. Gypsum and other salts are found near saline deposits in England, according to the source.
Okay, and finally, perhaps the most obvious one for many people, lakes as tourist attractions and health resorts.
Absolutely. The scenic beauty, the opportunities for recreation, swimming, boating, fishing, hiking along the shore, it draws huge numbers of people.
Famous resorts come to mind.
The source lists classics: Lake Geneva, Como, Lugano in the Swiss Italian Alps, Lake Placid in New York, Windermere in England, lakes in Sweden. Those beautiful glacial lakes in the Alps are major tourist hubs.
So it really is an incredible range of uses, from global shipping lanes and industrial powerhouses down to providing drinking water, food, minerals, flood control, climate regulation, and just beautiful places to visit.
They are woven into the fabric of human society and the natural world in so many fundamental ways. Truly multifunctional landscapes.
Right, let's try and wrap up this deep dive. We started with that simple idea: a lake is just a hollow filled with water.
But we quickly saw how much complexity lies beneath that definition. We've journeyed through this incredible array of formation processes.
Tectonic forces, glaciers carving and damming, volcanoes exploding, erosion, deposition, landslides.
Even beavers and human engineering playing their part. It's a testament to the Earth's dynamism.
And we saw they aren't just passive scenery, they're absolutely vital cogs in the machine of human civilization and natural systems.
Transport, industry, water, power, agriculture, climate, food, minerals, tourism. Their significance, as the source lays out, is just immense.
But there's that point we touched on earlier. The source reminds us that, geologically speaking, most lakes are temporary.
They have a lifespan. They fill in, they drain away. On Earth's time scale, they are transient features.
So here's the thought to leave you with. Given how profoundly we rely on these lakes for our cities, our industries, our food, our transport, what does their temporary nature tell us?
What does it mean that so much of our civilization is built around these features that are fundamentally fleeting in the grand scheme of things? How might our dependence on these transient landscapes shape our future, especially as we face environmental changes?
It's a fascinating tension, isn't it, between human timescales and geological timescales, between our needs and the planet's constant evolution. Something to think about.